Okay, let's look at the next problem because it's very similar to this one. So we have magnesium turnings are added to a solution of iron-free chloride. So, magnesium turnings. What's turnings imply?
Solid?
It's solid. So it implies that it's a solid. So that means it's going to be there. I'm simplifying this one a little bit. Added to a solution of iron-free chloride. What could we cross off for iron-free chloride?
The chloride?
Yeah, we can cross off the chloride. Why can we cross off the chloride?
Because iron's not silver, mercury, or lead.
Right, iron's not silver, mercury, or lead. Good. So we have that left over. The chloride is in solution, but it's not playing a role in the chemistry that's going on. Okay? And this is an old-fashioned redox problem. The iron and the magnesium are going to switch places with each other. So magnesium is going to go from an oxidation number of 0 to its oxidized form, and then iron is going to go to an oxidation number of 0. And so now we need to balance it. Well, you can see atomically it is balanced, but charge it is not. So we have to balance the charge as well as balancing it on the atomic level. So I have a 3+ charge on this side, I have a 2+ charge on this side. So I need to balance that with a 2-3 switch. So I put a 3 there, which gives me 3 magnesium now, so I have to have 3 over here. That still doesn't balance the charge. I have to put a 2 there, which means I have to put a 2 there. And then stop and go back. I've balanced atomically and I've balanced the electrically. Okay, so this is, in first-year chemistry, this is often called a single replacement reaction, where a more active metal is taking place of a less active metal. Magnesium is going to be more active than the iron on chlorine. So what we have forming in solution is magnesium chloride. So magnesium chloride is a soluble salt. So we write it dissociated. Chloride would be a spectator ion here. Iron would precipitate out. So now it's a solid. So that tells you what the answer to the question is. What will we observe is the magnet is brought near the reaction vessel. And that's kind of a clue as to what your product is going to be. And so what would we observe if we bring a magnet to the vessel? Iron is going to be pulled towards the magnet. And so you can say something. Iron drawn to the magnet or something along those lines.
Forgive me for my ignorance, but I don't understand why you would characterize like a reaction like that into like the normal single replacement reaction.
Because, well, let's write it out. If I were writing this in a first-year chemistry class, this is what I would write. You would agree with that? Okay, and then I would want to balance it. So I need to put a 2 here, and a 3 here, and a 3 there, and a 2 there. Okay? What's going on is this is a soluble salt. This is a soluble salt. What do they have in common is the chlorine. Since chlorine is soluble in both of the situations, it stays in solution. We never see it. We don't really know it's there. Chlorine almost acts like an iron delivery device. How do we get the iron into solution? We attach it to chlorine. And so because it's not participating in the actual chemistry that's going on, it's not participating in the reaction, we discount it. Okay? Chlorine is no different than, it's not quite a catalyst, it's a facilitator for the reaction. But it's not participating in the reaction, so we call it a spectator. Spectators are not included in net ionic equations because they're not part of the reaction itself.
Okay, so how would you determine the charges that you balanced on the top equation?
Okay, are you familiar with oxidation numbers? No, okay. Any element in its natural state is going to have an oxidation number of 0. Any element that is combined with something else is going to have an oxidation number equivalent to its ionic charge. So here the iron is combined with chlorine. It tells us in the equation it's iron 3 chloride, so we know that iron has an oxidation number of +3. Okay? We know in our product magnesium is now going to form a bond with chlorine, and when magnesium forms an ionic bond, it has a 2+ charge. Because iron and magnesium are changing places, iron is going to go from a +3 charge to a 0 charge, because now it's elemental iron in its natural state. So when we look at our charges, we have a +3 charge here and a +2 charge there. When you balance the equation on a molecular level, the charges are naturally going to balance when you balance the atomic. Okay? But when you're looking at the net ionic, the chlorine isn't there to help us. So we have to balance on the charge and not on the atomics. Okay? The charges have to be balanced. That is one thing there is no exception to that. When you balance the equation, the charges have to be balanced as well. And on a redox problem like this is a simple redox problem. On this type of problem, it's easier to balance. And this is where you may want to write the molecular, see what is the same from one side to the next, and cross it off. And then rewrite it in its proper form, because it makes it easier to balance it. Okay? Yeah, you can't have a net difference of electrons from one side to the other. That's not a proper form. Okay? Any other questions about this one? Okay. Let's look at the next one. You all look at the next one while I'm cleaning the board and see what you come up with.